This lesson is in continuation of the previous lesson where we discussed the discontinuities of a function graphically. Now in this lesson we are going to do the same algebraically. That is, we are going to figure out the discontinuities of a function when a function is defined by a formula. So I have taken this function as an example. So how do we detect the discontinuities of this function? If we remember the discussion from the previous lesson, we know that there are three requirements for a function to be continuous at a point A. A function should be defined at x is equal to a, that is, the point A should be in the domain of f. Then the limit of a function as x approaches a should exist. And lastly, the limit of a function as x approaches a should be equal to the value of f at x is equal to a. And this property is called the direct substitution property. So if any of these three conditions is missing for a function at x is equal to a, it cannot be continuous at x is equal to a. So in order to detect the discontinuities of this function, we are going to check that which of these three requirements is missing for this function at x is equal to a. So I'm going to start with the number 1. And why is that? Because I observed that on either side of this number 1, this function is governed by different rules. That is, for the values of x less than or equal to 1, this function is given by this rational expression. And for the values of x larger than 1, this function is given by this polynomial expression. So it might be possible that the limits of this function as x approaches 1 from the left and as x approaches 1 from the right are not equal. So it's important to check the limit of a function as x approaches a number on either side of which it is governed by different rules. So we'll start our discussion with the behavior of this function at x is equal to 1 and in its neighborhood. When x is equal to 1. Now it's clear that this function is defined at x is equal to 1. Because at x is equal to 1, this function is governed by this rational expression. And this rational expression is not defined only at the points where this denominator is 0, because division by 0 is not possible. We have already learned it in detail in the lesson number 3. And here it's easy to see that at x is equal to 1, this denominator is not 0, which means that this rational expression is defined at x is equal to 1. And this rational expression being a part of this function implies that this function is also defined at x is equal to 1. So the value of this function at x is equal to 1, that is f of 1, can be obtained by substituting x is equal to 1 in this expression. So when we substitute x is equal to 1 in this expression and we simplify it, it comes out to be 1, and it's quite easy to do that. So f of 1 comes out to be 1. But this function is defined at x is equal to 1 does not mean that it is continuous at x is equal to 1. This is just one requirement of a function to be continuous at x is equal to a. Now we need to check its limit as x approaches 1. So I'm going to use this to determine the limit of this function as x approaches 1 from the left. So if I write it as limit of this function as x approaches 1 from the left is equal to the value of this function at x is equal to 1, and which is 1. Do you agree with this? See, to understand this, you have to recall the lesson number 7a, where we discussed in detail that if a point is in the domain of a rational function, then its limit as x approaches that point can be determined by applying the direct substitution property. And that is what I did here. This is the direct substitution property for this rational function at x is equal to 1. Now while applying this direct substitution property, the reason why I considered only the left side limit of this function as x approaches 1 is obvious. See, this function is defined as this rational expression only up to x is equal to 1. So the role of this rational expression is over at x is equal to 1. So we cannot determine the limit of this function as x approaches 1 from the right using this expression. So in order to determine the limit of this function as x approaches 1 from the right, we have to use this polynomial expression, because this function behaves like this polynomial expression for the values of x larger than 1. So the limit of this function as x approaches 1 from the right is given by limit as x approaches 1 from the right, and we'll replace this f by the polynomial expression x squared plus 1, which is right here. And now it's quite easy to see that as x approaches 1 from the right, this x squared approaches 1. So 1 plus 1 is 2. So this limit comes out to be 2. So which means that the limit of this function as x approaches 1 from the right is not equal to the limit of this function as x approaches 1 from the left, and which implies that the limit of this function as x approaches 1 does not exist. Although this function is defined at x is equal to 1, its limit does not exist. Now can we tell that what type of discontinuity this function has at x is equal to 1? Recall the scenarios that we discussed in the previous lesson, one of which is right here. You can see for a function f, this function is defined at x is equal to a, and the limit of this function as x approaches a from the left exists, and the limit of this function as x approaches a from the right exists, but they are not equal. And because of their different values, a jump occurs at x is equal to a. And that's why this discontinuity is called jump discontinuity. So we have the same scenario here. At x is equal to 1, this function has a jump discontinuity. So x is equal to 1 is the case of jump discontinuity. Now, by looking at this expression, can we tell that are there more points where this function is discontinuous? So of course, yes. As we see that this part of this function is a rational expression. So it is not defined when the denominator is 0. We already discussed it when we were discussing this scenario. So let's quickly find out the points where this denominator is 0. So the denominator is 0 means that this x cubed plus 2x squared is 0. Now if we factorize this left hand side, we can take x squared common and we are left with x plus 2 inside, and then this is equal to 0, and which implies that x is equal to 0 or x is equal to negative 2. These are the 2 points where this denominator is 0, and when this denominator is 0, this expression will not be defined, and this expression being a part of this function implies that this function is also not defined at x is equal to 0 and at x is equal to negative 2. So when we substitute x is equal to 0 in this expression, it's easy to see that f of 0 comes out to be 2 over 0, and when we substitute x is equal to negative 2 in this expression, then f of negative 2 comes out to be 0 over 0. And both of these are not defined, which means this function cannot be continuous at these 2 points. Now let's see what types of discontinuities this function has at x is equal to 0 and at x is equal to negative 2. Let's first take when x is equal to negative 2. So we know that f of negative 2 is 0 over 0, which is not defined. But this alone will not tell us the type of discontinuity this function has at x is equal to negative 2. What we have to do is that we have to check the limit of this function as x approaches negative 2. So for that, I'm going to take the limit of this function as x approaches negative 2. So this can be written as limit of x plus 2 over x cubed plus 2x square as x approaches negative 2. Now at this point I would like you to recall the lesson number 7a, where we discussed in detail the method of determining the limit of a rational function as x approaches a number where function takes the form 0 over 0. So in order to determine this limit, I'm going to write down the upcoming steps directly without going into much detail. So I can write this limit as x approaches negative 2 of x plus 2 divided by. Now I'm not going to do anything new here. I'm just going to factorize this denominator, which we already did in the first place here. So the factors of the denominator are x squared and x plus 2. Now we can get rid of this x plus 2 from the numerator and from the denominator because x is not equal to negative 2. Rather, it approaches negative 2. So we are left with limit as x approaches negative 2 of 1 over x squared. Now it's easy to see that as x approaches negative 2, x squared approaches 4 and this quotient approaches 1 over 4. So this limit comes out to be 1 over 4. So what do we observe here? That although this function is not defined at x is equal to negative 2, its limit as x approaches negative 2 exists and it is equal to 1 by 4. So what type of discontinuity is this? Again, recall the scenarios that we discussed in the beginning of the previous lesson, and one of which I have right here. So where f is any function and this function is not defined at x is equal to a, but the limit of this function as x approaches a exists and it is equal to the number L. And we had seen that this type of discontinuity is called removable discontinuity. So we have the same scenario right here. So this is the case of removable discontinuity. So this function has removable discontinuity at x is equal to negative 2. Now the only point remains to discuss is x is equal to 0. So when x is equal to 0, we just saw that f of 0 is 2 over 0 and which is not defined. Again, this alone will not tell us the type of discontinuity this function has at x is equal to 0. We have to check the limit of this function as x approaches 0. So let's do that. So the limit of this function as x approaches 0 can be written as the limit of x plus 2 over x cubed plus 2x squared as x approaches 0. In order to see if this limit exists or not, I'm going to take exactly the same steps as I had taken in this previous limit. So starting from this expression up to this expression, everything remains the same for this limit as well. So I'm going to write down the last step directly, and which is the limit of 1 over x squared as x approaches 0. We can see that as x approaches 0, this x squared becomes smaller and smaller, as a result of which this quotient becomes larger and larger. So as x approaches 0, this limit comes out to be infinity. And we have already discussed infinite limits of a rational function in detail in the lesson number 7c. At this point, I would like to mention just one thing, and that is while going through the lesson number 7c, we had seen that in the case of infinite limits of a rational function, it's important to check the right hand side limit as well as the left hand side limit. But in this case, we are fine because whether x approaches 0 from the right or it approaches 0 from the left, this x squared comes out to be a positive number. So let's come back to this scenario. At x is equal to 0, neither this function is defined nor its limit exists. And because the limit of this function as x approaches 0 comes out to be infinity, which means that at x is equal to 0, the discontinuity is infinite discontinuity. So this is the case of infinite discontinuity. Now let's come back to the function right here. So after all this discussion, we found that this function is not continuous at x is equal to 1, at x is equal to 0, and at x is equal to -2. So what about the rest of the numbers? So this function is continuous on rest of the numbers. So let's see how. Let's first take the values of x larger than 1. We see that this function is governed by this polynomial expression for x larger than 1. And from the lesson number 6b, we know that the direct substitution property is satisfied on the entire set of real numbers for polynomial functions. So it means that it will also be satisfied for this polynomial function for x larger than 1. And in the previous lesson, we learned that the functions with the direct substitution property are called continuous at x is equal to a. So which means that this function, which is governed by this polynomial expression for x larger than 1, is continuous for all the values of x larger than 1. Now let's discuss the case when x is smaller than 1. We see that all the numbers smaller than 1 except x is equal to 0 and x is equal to -2 are in the domain of this rational function. And in the lesson number 7a, we learned that the direct substitution property is satisfied for the points in the domain of a rational function. So which means that the direct substitution property is satisfied for all the numbers smaller than 1 except x is equal to 0 and except at x is equal to -2. And as we know that the functions with the direct substitution property are called continuous at x is equal to a, so which means that this function is continuous for all the points smaller than 1 except for x is equal to 0 and except for x is equal to -2. So we have discussed the discontinuities of a function and its types algebraically. Now before I finish this lesson, let's quickly look at the discontinuities of this function and their types graphically. So I'm going to show you the graph of this function, which I have right here. So you can see that this is the same function that we discussed in this lesson. And here you see the graph of this function, where you can see that at x is equal to 1, this function is defined, but the limit of this function as x approaches 1 from the left is 1, and the limit of this function as x approaches 1 from the right is 2. So which means that the limit of this function as x approaches 1 does not exist. And because of the different values of this left and the right limits, there is a jump in the graph of this function at x is equal to 1. So that's why x is equal to 1 is a jump discontinuity. Again, at x is equal to -2, we see that this function is not defined. But as x approaches -2, the limit of this function exists. So this is a removable discontinuity. Now let's come to x is equal to 0. We see that as x approaches 0, the graph of this function does not approach a point. Rather, it approaches infinity. So we say that at x is equal to 0, this function has infinite discontinuity. So this is how we detect the discontinuities of a function and its type algebraically as well as graphically.